Welcome back to the Deep Dive. Today we're looking into something really changing the game in AI, context adaptation.
Right. It's basically the craft of making large language models, smarter after they're already trained.
Yeah, without touching those expensive weights.
hmm
Just by feeding them better input, better instructions, strategies, maybe external facts right in the prompt.
Exactly. And it's becoming, well, central to building AI systems today. You get speed, you get interpretability. It's much faster than fine-tuning.
You can add new knowledge fast, tweak behavior on the fly, but there's a catch, isn't there? How do you make sure that context, that sort of memory, actually improves over time?
And doesn't just become a huge, tangled mess. Yeah.
Which brings us neatly to ACE. That stands for Agentic Context Engineering.
hmm
And this framework, it kind of flips the script. It says context shouldn't be some short summary.
No, quite the opposite. ACE treats it like an evolving playbook. Think detailed, structured knowledge that's designed to grow and get refined, scalably.
So today, we're diving deep into the source material on ACE. We want to see how it manages to fix two really big problems that, well, tripped up earlier methods.
Right. And the results are pretty striking, big performance jumps, but also, crucially, much lower costs.
Okay, let's get into it. Those two core problems ACE tackles. What's the first one?
The first one is something called brevity bias.
Brevity bias.
Yeah, you see this a lot with prompt optimization techniques. Think of systems like GPA generalized prompt auto-generation.
Okay.
These systems try to find the best prompt, but they often end up favoring instructions that are really short in general. Conciseness wins out.
That feels wrong somehow.
Yeah.
I mean, for humans, being concise is usually good, right?
Right.
Shows you understand something deeply.
It does for us, yes. But for LLMs, especially doing complex tasks, it's different.
How so?
Well, this bias towards brevity, it pushes the optimizer to ditch really important details. You lose specific heuristics, step-by-step guides for using tools, maybe examples of what not to do based on past mistakes. The source material really argues that LLMs, unlike us, actually thrive on long, rich contexts. Give them the detail, and they're surprisingly good at figuring out what's relevant when they need it. Don't pre-summarize their playbook for them.
Okay, so try to be too brief. That pressure to compress early on, that leads to the second problem, which sounds, frankly, pretty bad. Context collapse.
It is bad. Context collapse happens with methods that use what's called monolithic rewriting.
Monolithic rewriting.
Yeah, so every time the system learns something new, it tells the LLM, okay, rewrite the entire context from scratch, but include this new lesson.
Oh, wow. So if the context is already huge.
Exactly. The model inevitably starts summarizing, compressing things down. It loses information.
It sounds like editing a massive document by rewriting the whole thing for every single correction, and you just know you're going to accidentally delete important stuff.
That's a good way to put it. And the evidence they found is, well, dramatic. They used the App World benchmark, that's a test suite for AI agents doing tricky tasks across different apps. At one point, an agent had built up this context, like 18,000 tokens strong. Huge. I was doing well, about 66.7% accuracy.
That's a lot of detail, yeah. Packed with strategies, probably.
For sure. But then, the next learning step. Monolithic rewriting kicked in. Collapse. The context just shrank massively, down to only 122 tokens.
From 18,000 to 122, seriously. What did that do to performance?
Killed it. Accuracy dropped sharp, down to 57.1%.
Ouch. Okay, wait, 57.1. How does that compare to just not adapting the model at all, like the baseline?
Worse, the baseline with zero adaptation was 63.7%.
No way. So the learning actually made it significantly worse than doing nothing.
Precisely. Context collapse didn't just stall progress, it actively undid learning. That's the systemic failure ACE is designed to prevent. The whole idea is keep the playbook detailed, preserve that knowledge, don't compress it away.
Okay, that makes the why crystal clear. So how does ACE pull this off? Let's get into the mechanics. You mentioned agentic architecture.
Yeah, it borrows from earlier agent designs like dynamic cheat sheet, but ACE uses three specialized roles, like distinct agents working together.
Like a little team. Keeps things focused.
Exactly. It avoids making one single LLM do everything, which helps with stability. First, you've got the generator.
The workhorse.
Pretty much. It's the LLM actually doing the task, generating the reasoning steps and the answers.
Okay. Role number 2.
The reflector. This one's job is to look at what the generator did, the successes, but especially the failures, and figure out why. It distills those observations into concrete lessons.
Like a quality control or review step. And the third?
The curator. This is the knowledge manager. It takes the lessons from the reflector and integrates them into the playbook.
Ah, and this is where ACE avoids the collapse.
Yes, this is key. It leads to the first big innovation, incremental delta updates.
Delta updates, like software patches.
Sort of. Instead of seeing the context as one big text blob to rewrite, ACE treats it as a structured list of, well, bullets. Itemized point strategies, failure modes, code examples, rules, things like that.
Okay, so structured data, not just prose.
Right. And when the curator gets a new lesson, it doesn't rewrite the whole list. It just generates a small delta context, maybe a few new bullet points or an update to an existing one.
Like adding sticky notes or editing specific lines in the playbook.
Exactly. And here's the critical part. Merging these deltas into the main playbook isn't done by the LLM.
Oh, how then?
It uses simple deterministic logic, like basic programming code, append this new bullet, update that one. Because the LLM isn't doing the merge, you guarantee that old validated knowledge doesn't get accidentally deleted or mangled.
That sounds much more robust, like version control for AI memory.
It's like,
But
you know.
hang on, if you're just appending stuff, doesn't the playbook just get bigger and bigger indefinitely? Won't that become slow and expensive?
Good question. That's where the second innovation comes in, the glow and refine mechanism.
Grow and refine.
Okay. So ACE deliberately lets the context grow. New bullets get added, existing ones might get tweaked. But it also has this refine step to keep things tidy.
How does it refine?
It uses semantic embeddings, basically a way to represent the meaning of each bullet point numerically. Then it can compare bullets and find duplicates or near duplicates.
So it deduplicates based on meaning, not just exact wording. Keeps the playbook from getting bloated with redundant advice.
Precisely. Comprehensive, but still relevant and compact. And the examples they show, they're really specific. It's not just vague advice.
Like what?
Well, in the app world example, the playbook might have a section like strategies and hard rules with things like always get contact info from the actual phone contacts app, not somewhere else, or make sure you compare dates correctly, not just as text strings.
Very concrete.
And maybe another section with useful code snippets for common actions. It's that level of detail that gives the agent an edge.
And that's exactly the kind of stuff that gets lost with that brevity bias you mentioned earlier.
Exactly. Traditional prompt optimization would probably erase those crucial details.
And this ACE approach, it works for setting up a system initially, like offline.
Yeah.
And also for learning on the fly, online.
Yep. You can use it to optimize a static system prompt before deployment, or have it update an agent's memory during runtime as it encounters new situations.
Which brings us to the results. Does all this clever engineering actually pay off? What are the numbers?
Okay, this is where it gets exciting. On that App World benchmark for agents, ACE gave an average performance boost of 10.6% compared to strong baselines.
10.6% over things like just using examples, ICL, or that GPA optimizer.
Correct. But here's the really eye-opening part. They took a relatively smaller open-source model, DeepSeek v3.1, paired it with ACE in a React agent setup,
Okay.
and it matched the average score of the top-ranked agent on that benchmark at the time. That was IBM's CUGA agent running on the much larger proprietary GPT 4.1 model.
Hold on. So an open source model, just by having this better ATE context system, performed as well as a top-tier agent using GPT-4.
That's what the results showed.
Wow. That really suggests the way you manage context, the memory architecture, is becoming just as important, maybe more important in some ways, than just having the biggest base model.
It really points in that direction. And another key finding, ACE learns, well, just from natural feedback.
Meaning
Meaning it doesn't necessarily need humans labeling data perfectly. It can improve just by seeing if the code it generated ran successfully or through an error. That's huge for self-improvement in the real world.
Okay, so strong results for agents.
Yeah.
What about other areas, like reasoning?
They tested it there too. On complex financial analysis tasks, think understanding financial reports using things like XBRL rules, the standard for financial data tagging.
Right, very specialized knowledge needed there.
Yeah. ACE delivered an average gain of 8.6% on those tasks too.
So it's flexible, works for planning and knowledge-intensive reasoning.
It seems so. Now, fairness requires mentioning a limitation they flagged.
Okay, what's that?
ACE, like any system learning from feedback, depends heavily on the quality of that feedback. If the signals it gets the ground truth, the success-failure outcomes are noisy or unreliable, well...
Garbage in, garbage out. The curator can't learn good lessons from bad data.
Exactly. Performance can degrade if the feedback loop is broken, so that's a critical dependency.
Makes sense. But assuming you have decent feedback, the efficiency gains seem like a massive selling point.
Yeah.
This isn't just about better performance, it's about cheaper performance.
Absolutely. Those incremental delta updates, avoiding the full LLM rewrites, it slashes the computational cost.
How much are we talking?
The numbers are pretty wild. Compared to other adaptive methods like dynamic cheat sheet, ACE showed 86.9% lower adaptation latency on average.
So it learns nearly 7 times faster.
In terms of update speed, yes, and the cost.
Right.
An 83.6% reduction in token dollar cost for that learning phase.
Wow. Over 80% cheaper to run the learning process.
Yeah, and even when used just for offline prompt optimization compared to GPA, it cut the time needed by over 82%.
Okay, that's huge. It really reinforces that idea. You might not need the absolute biggest model if you have a smarter, more efficient way to give it the right knowledge.
It strongly suggests that scaling capability doesn't have to mean scaling costs exponentially anymore. Smart context engineering can bridge the gap.
So, wrapping this up, what's the big takeaway here? ACE seems to be showing that the future isn't just about giant models.
Right. It's also, maybe even primarily, about how we manage the knowledge we give them. These structured, evolving playbooks seem key.
And you mentioned implications beyond just performance, something about compliance.
Yeah, that's a really interesting side effect. Because ACE keeps knowledge in these distinct, itemized bullets, it makes things like selective unlearning feasible.
Unlearning, like making the AI forget something specific.
Exactly. Think about privacy rules like GDPR in Europe or CCPA in California. They have right to erasure clauses. You need to be able to remove specific user data or outdated info from your AI's knowledge.
Which must be almost impossible if your context is just one giant monolithic prompt that gets rewritten all the time.
Very difficult, yeah. But with ACE structure, you can potentially target and remove specific bullets related to that information. It's much cleaner.
So it's potentially more future-proof from a legal and regulatory standpoint, too? That's clever.
And you combine that with the trend of infrastructure getting better and cheaper at handling long contexts, things like KV cache improvements.
Right. The cost per token for very long inputs is dropping.
So if giving the model a really rich, detailed context becomes increasingly cheap, does that shift the whole optimization focus? Will we see less emphasis on costly fine-tuning runs that take weeks or months?
And more focus on rapid, cheaper, continuous context engineering using